because this p-value, 0.0294, is less than our alpha, which the problem told us was 0.03. Okay. Let's quickly do part C as well. So now we want to find a confidence interval, or a 90% confidence interval. So this is part C now. So finding a 90% CI with a population proportion P. And so we start with our formula. And our confidence interval is given by our estimate, which is p hat, plus or minus that margin of error, which is z star times the square root of p times 1 minus p over n. But the whole point is we don't know what this p is, so the best thing we can do is use p hat instead. Okay? And so now this is mostly plug and chug, so we know what p hat is from last time. We also know what n is. What about this z star? Yep, Sophia?
Would it be 1.645?
So you got that z star is 1.645. And how did you get that answer?
I memorized it.
Okay, I think that's one approach. So yeah, for 90% confidence interval, the corresponding z star is 1.645. The reasoning, like the way you get that is, you should think about having a standard normal distribution where the area in the middle is C, and your z star is the right boundary of that thing. So if you figure out what this is, it's 1.645. Right, in this case, the area to the right, the area to the left is always going to be C plus 1 minus C over 2. So if you work this out, it ends up being 95%. And the thing that's to the right of 95% of the area is 1.645. Okay? So, yeah, the only real tricky part is figure out what this z star is. And after that, you just plug in your numbers. In this case, I got 0.06 plus or minus 0.028. Okay. So this leads into the final thing I want to talk about from chapter 20, which is, what if instead of fixing this number n and getting a margin of error, what if you want to go backwards? Right? So for instance, maybe maybe you're the potato chip company and you want to look into different potato suppliers. Let's say we want to find a confidence interval that is narrower without sacrificing on the confidence level. Okay, so the question is, what what if we wanted a 90% confidence interval with margin of error equal to 0.01. Right, in this case, our 90% confidence interval had a margin of error of 0.028. Now we want a narrower confidence interval with the same confidence level. So what does that mean about our sample size?
It's larger.
To get a bigger sample size. Right? To get more precise confidence intervals, you always need more data. So the question is, how many potatoes must we sample in this case? Good. And so, well, we can do this by solving this thing for n. So, remember the margin of error. Let's just call this letter E. So we have the formula E equals Z star times the square root of P times 1 minus P over N. Okay, so this is where P is the actual population parameter. And so remember, this is now like a new problem. We don't have the data from before, so we don't have any P hat yet because we haven't taken a sample yet. We don't even know what our sample size has to be yet. So we don't have any P hats or anything. And so, right, in this case, we want to solve this thing for n. Question?
On the previous one that we did, it says like the portion of potatoes in the trunk that have feedback. So does that mean that your n value changes to 12 instead of 200 when you plug it into that?
Oh, no, in this case, you still use n equals 200 for part C.
So is the 12 just like extra information that we give you?
So you use the 12 to figure out what P hat is. P hat is the number of successes, which is 12, over the sample size. And the sample size n is the same as before, it's still 200. Okay. So basically, we want to rearrange this thing to be n equals something. And so, well, we just use some algebra. E over Z star is the square root of P times 1 minus P over n. So this tells us that E over Z star squared equals P times 1 minus P over n. We can flip both fractions to get Z star over E squared equals n over P times 1 minus P. And finally, if we multiply both sides by this denominator, we get Z star over E squared times P times 1 minus P is equal to n. Okay? So this is the formula for finding how large of a sample size you need for these proportion tests. Now, if we try to apply this to the problem we were doing, we run into some trouble pretty quickly.